Hi, we're going to take a look at equations of circles right now. So one thing we can find equations for, of course, are lines on the Cartesian plane. And we know that the equation looks like y equals mx plus b. And in order to determine that equation, we need a slope and we need a point on the line. Okay, we're now going to move up to circles. Okay, so slightly more complex objects. So we might expect the equation to be a little more complicated, but what we want to determine is what is the minimum information needed. Now, it would make sense that we would need the center of the circle, okay, and we would need to know how far the points are from that center, so the radius. Okay. Now, when we were developing the equation of a line, we tried to focus on what was common to all the points on the equation line, and we realized that the rate of change, okay, or the slope remained constant regardless of which 2 points we use to determine the slope. Okay, so what we want to do now is figure out what is the same with respect to all points on this line. And of course, what they all have in common is that the distance to this center 5, 6 always has to be equal to 4. Okay, so that's what we're going to use to come up with an equation to describe all these points on the circle. We're going to use what they have in common. Okay, now since I want to describe any point on the circle, I don't want to take any specific one. Okay, I want to use variables to describe those points. Now I say variables because any point will have both an x and y component. So if I pick some random point on the circle, okay, but I want this to represent any point, could have been this one, that one, any point on the circle, I'm going to call it x, y. I'm going to keep the x and y components variable. Okay, and since I'm going to work with what's common to all points, excuse me, on the circle, okay, it doesn't matter whether I'm working with this one or that one or the other one. Okay, and what they all have in common is that the distance from the center to that point has to be equal to 4. So since it's a distance that's common to all these points, I'm going to work with the distance formula. Okay, so let's recall that the distance formula is the square root of the difference of the x components, so x2 minus x1 squared, oops, that's 1, okay, plus y2 minus y1 squared. Okay, now in this case here, we know that for any point xy on the circle, the distance has to be 4, okay, and I'm always finding the distance to this center point 5, 6. So I can write here x minus 5 squared plus, and then y minus the y component of the center, so 6 squared. And what we have now is an equation that relates the x and y components of the circle in the same way that y equals mx plus b relates the components of any point on the line. Okay. Now normally we prefer not to have square roots in an equation if we don't need to, so there is a way to remove this square root, and that would be by squaring this side of the equation. But of course, if we do it to one side, we also have to do it to the other side. So we end up with 16 equals x minus 5 squared plus y minus 6 squared. Okay, and this is the equation that we use to describe the circle, or all the points on the circle, with radius 4 and with center 5, 6. Okay, but ideally I'd like to have an equation that works for any circle, so with any center and any radius. Okay, so instead of working at the specific center 5, 6, let me give it, again, let me use unknowns to describe any center. And the letters we're going to use are h and k. So h will always represent the x component of the center, k will be the y component of the center. And instead of working with a specific radius of 4, I'm just going to use a variable radius r. Okay? But we can see that, again, for any point on this circle with center hk and radius r, we have the same relationship. The distance between the point and the center is always the same. So I can repeat exactly what we have here, that r, our distance between a point and the center, is just the square root of x minus, now here we're going to use the variable h squared, plus y minus the y component of the center squared. And as before, we can get rid of the square root by squaring both sides. So we end up with r squared equals x minus h squared plus y minus k squared. Okay, and this is the equation that describes all points on a circle of center hk and radius r. Okay, so let's write that down as a note. So a circle with center at the point hk and with radius r can be modeled by the following equation: x minus h squared. So normally we write this portion on the left hand side, plus y minus k squared equals r squared. Okay, so in the same way that to find the equation of a line I need a slope and a point, in order to find the equation of a circle I need a center and a radius. Okay, so let's take a look at a couple of easy examples, and then there's a couple of tougher questions for which I've posted the solutions to. So from the equations of circles sheet, I've posted solutions to questions 5 and 6. Okay, well, let's take a look at a couple of examples here. So let's say I want to find the equation, okay, of the circle with center, let's say negative 2, 5, and radius, okay, let's make it a little more interesting, let's say root 10 units. Okay, now this one here gives us the exact information we need to write the equation of the circle, because they've given us the center and they've given us the radius. Okay, so all we have to do is plug this into the equation. Okay, so here we have x minus the x component of the center, negative 2 squared, plus y minus the y component of the center, 5 squared, is equal to the radius squared. And if we clean this up, we end up with x plus 2 squared plus y minus 5 squared equals root 10 squared is just equal to 10. Okay, so this equation describes all the points of the circle that has a center negative 2, 5 and the radius root 10. Okay, now sometimes it's not given quite so explicitly. So, another type of example that's very common is you might be given points, okay, that describe a diameter of the circle. So the question is, how can you find the equation? Well, you need a center, and since this is a diameter, the center would just be the midpoint between the points which define the diameter. And then in order to find the radius, well, once you have the midpoint, you could just find the distance from one of these points to the center, or alternatively, you can find the distance between the 2 points and divide by 2, since that would be the diameter, so half of that would be the radius. So there's a couple of those questions on the sheet. Okay, let's take a look though at a different example here. Okay, so let's say let x minus 3 squared plus y plus 6 squared equals, say, 8. Okay, be a circle. Now, of course, if you take a look at this, you should be able to tell that the center of this circle would be 3, negative 6, okay, in order to get that y plus 6, and the radius would be square root of 8. Okay, so just a little below 3. Okay, what we want though is if x is equal to 4, determine the possible y values. Now notice here I'm saying the possible y values. Okay, this is something that's different from a line. On a line, you'd only ever have one y value for every x value. But say this is your circle, okay, and say this is x equals 4. You notice that there's 2 possible points on the circle that have an x value of 4. Okay, so it's not too far to realize that you might actually have possible y values. But let's see how the algebra works out. Okay, So like I normally would do if I have the equation and I'm given one of the variables, I'm just going to replace that in the equation. So here, wherever I see an x, I'll replace it by 4. Okay. I still don't know the y value, so I'll leave that as an unknown. Okay, and now let's simplify. 4 minus 3 is 1, so we have 1 plus y plus 6 squared equals 8. And this is where we have to decide how to proceed. Okay, it might be tempting to square this, to write y plus 6 times y plus 6 and then expand. The problem with doing that is you'd end up with a y squared term, but you'd also end up with a 6y term. And at this point here, we don't have the tools to solve equations that have both a y squared and a y. Okay, but we'll continue going because I think we can actually solve this using opposite operations. Okay, so let's go ahead and do that. So we're going to do reverse bedmass, bring that 1 to the other side. So y plus 6 squared equals 8 minus 1 is 7. Okay, the opposite operation to squaring would be the square root. So I'm going to take the square root of both sides. And this now is where, again, I need to be careful. So I'm going to just do a little something on the side. Let's say you have the equation x squared equals 16. Okay, well, clearly x equals 4 would be an answer. When you think about it, there's a second answer. Okay, x could also be equal to negative 4. Okay, because negative 4 times negative 4 is also equal to 16. Okay, so you got to keep in mind that when you're taking a square root to solve an equation, you have to consider that there's both a positive possibility and a negative possibility. Now in grade 9, you didn't normally do this because you were often taking the square root to solve a Pythagoras problem where you were interested in the length. So that's why you didn't consider the negative solution most of the time. However, here, it's certainly possible that the answer could also be negative. So when we take this square root, I have to consider that it could be the positive square root of 7 or the negative square root of 7. So now when I solve for y, I've got two possible solutions that I can get. I can have this positive square root of 7 and then subtract 6, or I could be working with the negative square root of 7 and subtracting 6. And so these are my two possible values for y. Okay, so like I said, there's a couple of more examples posted, so we'll leave this for now.